now we're all sorted. I'm going to stop the 4 breaks.
Good evening. I'm sorry for the technical interruptions. Well, first of all, thank you very much for YOW and DDD Perth, and especially also for Bank West for hosting this and inviting me over to Perth. It's in fact the first time I've been in Perth, so great to see you all. So now about this functional programming thing. Well, let's take a step back. Let's not start with functional programming. Let's start with more slowly. So, in the 60s, when Edgar Dijkstra introduced structured programming, there were a lot of developers who called the ideas he put forward academic and not very convincing. But today, when we teach programming, I mean, nobody would even entertain the idea of doing something different. A little later, when people like Alan Kay introduced object-oriented programming and languages like Smalltalk and C++, again, people said, well, that's kind of cute, but hey, I can write my stuff in C and it's just okay. So now we are again in such a paradigm shift in our industry. And it's all the same things all over again. Isn't functional programming a bit too academic or impractical? Well, maybe it's okay for those ninja rockstar programmer people, but not for the average developer. And also it's inefficient and definitely way too complicated. So it looks like we are going through these phases, right? Interestingly, it's not just us. It turns out that a smart person, a professor for communication studies, Everett Rogers, he's written a book actually called Diffusion of Innovation, and this is a theory which has been corroborated by business scientists over and over again. Whether it's railroads, dishwashers, smartphones, any kind of technological invention, they all propagate through a social group in more or less the same manner. So if you look at these curves, the blue curve is the number of new people adopting a technology. And the yellow curve is the sum of all people who've adopted this technology. So now, when we look at functional programming or any developer technology, then the question is, of course, what does it mean for somebody having adopted? Like, do you have to be a hardcore Haskell programmer? Or isn't it, if you use React in JavaScript, I mean, you're doing functional programming, so shouldn't that count? So we may wonder, where are we here on this scale? So I would say we are kind of in the transition phase between early adopters and early majority. And that's important because these different groups of people, they adopt a technology and innovation for different reasons and in a different manner. So if you're interested in kind of promoting something, then it's very important that you understand where you are and you understand what the mindset of the people you're talking to is. So let's look at these groups one by one. So the innovators when we're talking about programming languages, these are people like programming language researchers, the people who design and standardize the programming language, the people who write the compilers, the ecosystems, the base libraries, the initial tools. These are very, very people who are very happy to take risk, right? They define a new programming language, go to the extent of writing an entire compiler just to prove to the world that it's better for some measure of betterness, right? So that's high risk. They're also usually, in the case of PL, these people typically have a background in programming language theory, they know compilers, maybe quite a lot of math background. So it's a particular type of person, right? And then when you go to the early adopters, the early adopters usually have a good connection to the innovators, and those are the people on your team, on your dev team, who take something, a new programming language, and do their hobby project on the weekends, kind of upskill themselves until one day they go in a meeting, I think we should use this new technology. These are the people who bring something new into an existing group, right? They are not like the innovators, they didn't make it up themselves, but they also typically, they have good connection to the innovators, they're happy to read a research paper with lots of math in it, spend a long time to understand it, in order to then be able to be the first person in their peer group to say, I understand this, I can show you how we can do everything better. Right? Still prepared to take quite a lot of risk, a lot of investment before there's a payoff. Right? But they don't want to start from scratch. They wouldn't want to write a new compiler. They want a compiler, tools should be kind of okay, but they're happy to figure it out. And then the early majority, that's the rest of the team. They're going like, we have to solve a problem, right? Is this stuff ready for production? Can we use this? Right? So that's a totally different mindset. And they don't want to sit, read a research paper, read up about some math behind it. They just want to use it. If it's not ready to be used, if it's not ready to solve a problem, then rather let's wait a little longer until people have solved these problems. Okay? So how do we get the early majority into functional programming? So now, I mean, I can kind of guess the answer already from earlier questions being asked, but who would say, well, I'm doing functional programming? Okay, a few people. That's not too surprising because it kind of was probably going to be the inverse of people wanting to do functional programming introductory course. Okay, so I'm talking about you people. All right. So how can we make functional programming attractive to you, or how can we communicate why it's interesting? Right? So of course there's also the other half of the curve, but I'm not interested in that tonight because this is a problem for another day. So one reason why I'm saying all this is something Amy already mentioned. We've got Lambda Jam. Sorry, it's in Sydney. I know it's far away. I just noticed it's far away. I spent 5 hours on a plane. But it's a really fun conference. Now, so until now, the idea with Lambda Jam has always been to be a conference basically for the early adopters. All the talks are kind of what we call intermediate to advanced level. The idea is people who have maybe spent the weekends kind of trying to learn a functional programming language. Now at the point where they understand the basics, but they want to get to the next level in order to introduce it to their team. That was the purpose of the conference. That was always the design. If you're one of these people, you still got another 5 days to submit something, please do. Everybody who raised their hand earlier when I asked about functional programming. But as Amy also already explained, there's something new. We are doing this for the first time, the Welcome to FP Day. So this is a day of workshops, a few workshops, where the idea is to take it a bit slower, take our time to introduce people who haven't got that much know or not that much experience with functional programming, and but are interested, and get them, show them the basics, basically. So you can use functional programming if you like to, and at least you know what people talk about, and you can talk as well. And also, of course, in order to get you to the point where you can enjoy the other 2 days of the conference. That's why the welcome day is the day before the 2 main conference days, right? And yeah, I'm going to give an introduction to functional programming, and what I want to do today is tell you a little bit about the idea behind it. So the question is, what's wrong with the way functional programming has been presented so far, and why, and how can we change it, right? So why am I here? Well, the reason I'm here is because together with Gabriele Keller, we at the University of New South Wales, we've been teaching functional programming and Haskell to literally thousands of people. That's from first-year students up to postgraduate students, people who are experienced developers and do a master's degree or postgraduate degree. So while doing that, we've put quite a lot of energy in figuring out how can we teach functional programming properly. We've done a lot of surveys to get feedback on what works, what doesn't work, what's the right approach, and so on. So we've distilled a lot of what we learned into this thing, which is a free online tutorial on Haskell. So if you want to learn Haskell and you don't want to wait until the Welcome to FP Day for Lambda Jam or for Tony to teach you in a few weeks, well, you can hop online and just get going. And so this is a general tutorial. You don't have to have any previous knowledge of functional programming. It includes screencasts of live programming, so you can see what happens and so on. So that's the background. That's where I'm coming from, basically. So I'm not working at UNSW anymore, but I did that for quite a while. So let's return to our earlier story about these innovators, early adapters, early majority. So I think one reason why functional programming is kind of mysterious is because the communication, a lot of the communication has been between these groups, the innovators and the early adopters. And they tend to speak in their own language. And if you just hop in the middle of it and you listen, it just makes no sense whatsoever. So why is that? So there are a few reasons. So one reason, which actually is quite general, if you look at how programming languages are taught, very often it's done in a very language construct for language construct kind of way. It's like, today we are going to do while loops, and next week we are going to do class definitions. But that's wrong. It's kind of guided at the language. What you really want to teach is the concepts. It's like if you're supposed to learn to drive, and today we are going to do the steering wheel, and tomorrow we are going to do brakes. What, do you want to practice driving? Come on! Right? So the individual bits, they don't tell you that much, and especially going by programming language constructs, not very helpful. So there's a nice paper by Felaisen, Findler, Flat, and Krishnamurti, who did a lot of work at a few universities in the US, Rice University Northeastern, about generally teaching programming languages, and they make this point quite clearly. If you're interested in teaching, learning programming, it's an interesting paper to read. So that's number one. Number two, a grave mistake, which innovators like to do over and over again, is look at the innovator. That person has been there when the language was invented. They solved all the problems. They make 50 mistakes until they got to the right solution. Now, when they tell you about it, they're very keen to tell you the whole story. For them, it's the whole thing, right? But you don't care. You want to know what's the goal of the journey, right? You don't want to know the historic way of getting there. So in the Haskell community, as an example, there's this thing, do you know category theory? Who knows category theory? It's a rather abstract branch of mathematics. So I'm not surprised that you don't know about it. But there's an Italian mathematician slash theoretical computer scientist. His name's Eugenio Moggi. He is a very smart person. He understands category theory in contrast to me. And he figured out a way to use that abstract mathematical, those concepts, to still quite mathematical kind of formalize the semantics of all kinds of programming languages, not just functional programming, imperative programming, object-oriented programming, and so on. It was really breakthrough, really significant work in the area of semantics of programming languages. And then there was a second very smart scientist, brilliant scientist, Phil Wadler. Some of you may have heard of him. He took those ideas from Moggi and he figured, wow, you can't just model the semantics of programming languages. You can use these ideas to structure functional programs. And since then, people have figured out how to structure C++ and other, it's not actually constrained to functional programming, how to, a very general principle for structuring programs, software. And you may have heard this kind of thing, monads. One of the scary words in FP land, right? So when people are asked, can you explain monads to me? Then very often they go, well, monad is a term from category theory. At that point, everybody runs away. Because who knows category theory? We had one person in the room, okay. And there's this kind of half joke, half truth in Haskell land is kind of to kind of make that point is, well, a monad is just a monoid in the category of functors. What else do you need to know? It's not very helpful, right? But the problem is exactly this, explaining things in a historical way. Well, the concept of a monad in functional programming originates over a few steps from category theory. So people who know about this, they go, oh, well, we have to start at the beginning. But really, most people don't want to know about that. They just want to know, how can I structure my program? So you have to explain things in terms which are accessible to the student, right? Which stand on their own without the historical explanation. That's, I think, one of the biggest obstacles, one of the biggest problems which makes a lot of the existing writing on functional programming inaccessible, because it takes this historical approach. All right, so that's the innovators. How about the early adopters? So early adopters, they are further removed from the innovation, but they still, because they're happy to invest quite a lot to learn something new, they're happy to go to these abstract levels to read about maybe even category theory, something like that, and understand things from there. But that doesn't work in general. So they have a hard time communicating very often to, for example, their team. Why is it useful? How does it work? Because the explanation just comes from the abstract instead of from the concrete. What you really have to do is you have to lead with examples. So, for example, coming into the room saying, well, today I'm going to explain to you what parametric polymorphism is. It's not very helpful, because you have no idea what parametric polymorphism is. So why would you even care? It's the wrong starting point. What you have to do, you have to start explaining why. by way of some examples. So for example, you could have in your favorite programming language a few different examples of functions computing the length of a list for lists of different element types. And go like, look at that code. Looks pretty similar, right? Why do I have to retype that? So that gets you to a problem statement. You go like, can't we reuse that code? Can't we kind of write less code? Because it seems like it's all doing the same thing. That seems superfluous. Now from there, you can introduce a generic function. And then you do that a few more times, and then you can come to the general concept. Parametric polymorphism, or sometimes mistakenly called generics. Generics just too general. Generics means everything. It has too many meanings, I mean. Anyway, that's not my point. My point is we need to go from the concrete to the abstract, not the other way around. So in particular, that answers the question like, do you have to be a math superhero, a math whiz, to understand functional programming? No. Functional math can't be the starting point. In the same way as category theory can't be the starting point for structuring programs. But I think when everything is said and done, maybe in 10 years we can settle this question, I think the biggest contribution of functional programming to programming will have been that it has brought math and software development further together. But for that, it can't be the case. We can't require everybody to be a mathematician and then start to apply this to software engineering. That makes no sense whatsoever. If what I'm saying is correct, then through development, software development, program development, we have to see structures which then we can lift to a level where we can talk about them in a more abstract way. And there's actually good evidence for that. Who knows about this Bootstrap program? And I don't mean the web framework. So this is a program which actually came out of these courses of these people I mentioned earlier, Filets Net Hour, who wrote this paper, this nice paper about teaching. And from the course design they developed, a few universities got together and they said, well, if this holds water generally, then shouldn't it be possible to get kids interested in writing exciting software and teach them math that way? And so what they did, they developed this curriculum for children between grade 6 to grade 12, and they went especially to schools in lower social economic regions where usually STEM teaching is quite difficult, and they taught them coding in a functional language called Recursion. And they did all kinds of things, but they kind of did a very principled approach, driving towards algebraic principles. And lo and behold, not only did those kids learn coding, their algebra score suddenly went up. And they did this in quite a few schools by now. It's quite a big program. You can read up about it on that webpage. And so they gathered a lot of evidence that this actually works. It even works at the middle and high school level. Okay, so why shouldn't it work for us? All right. But then there's always this question. What about all these fancy words? I said two already, like parametric polymorphism. Come on, can't you call it generics like everybody else? So this terminology, I think, is not just, is here to stay. Why? Well, let me give you an example. Do you know what's common to all these words, terms? Somebody knows.
They used to describe a monad.
Yeah, they've been proposed as alternatives for a monad. Now that I've told you those other words, do you have a better understanding of what a monad is? So really, the name wasn't the problem, was it? And there's actually, I think it's wrong to try to reinvent all the names, change all the terminology. Why? Okay, we have to learn these new words, and some of them may be a bit weird. But first of all, that's the case for any programming language, right? Do you know what I have to read it off because I can never remember it. What a protected, abstract, virtual, base, pure, virtual, private destructor is? And if not, do you program C++ and you don't know? Come on. So every technical domain has its terminology. That's just normal. And when you learn that domain, you learn the terminology. Goes hand in hand. And if we just change all the terminology around, we do people who learn this stuff really a disservice. Why? Because the learner should be able to graduate to become an expert, right? And if you use different terminology, then at the end of the day, you may know everything, but you don't know how to talk to somebody else who's already been expert. You don't know how to read a research paper or any of the more advanced material because it uses all different terminology. That makes no sense. So I think let's just learn the terminology on the way while learning the concepts, because the terminology is not the problem. All right, so I said a lot of things about what we shouldn't do or how we shouldn't present functional programming, general program development. So I also want to make 4 positive points, okay, 4 things. So we already talked about examples, but I want to demonstrate how we can use examples to teach abstract concepts. And it's really important to give guidance, especially in functional programming. So one of the killer features of functional programming is that it's very easy to build abstractions. But that also means it can be a bit intimidating in the beginning to know how to do this. And you need kind of patterns of how to do that. You can't just do it freeform in the beginning. And then with development tools, we can help by having tight feedback loops, and we can use visualizations, especially in functional programming. When you don't have side effects, visualizations convey really good intuition. So I want to show you examples of that. So let's start with the examples. Typically, when you teach functional programming, the first concept which causes trouble is recursion. That's the case for people who haven't programmed before. But it's also the case for people like you who are experienced developers. In fact, so in our experience, when teaching functional programming to first-year students, the students without programming experience, they usually didn't have a hard time understanding Haskell. It's the people who already did Visual Basic who had a problem. That's interesting. But I'm digressing. So let's look at recursion. A typical kind of wrong way of explaining recursion, kind of doing let's start with the mathy kind of bit, is the following. Recursion is it's super powerful, but it's also really simple. This definition, incomprehensible Haskell code, captures everything about recursion there is to say, at least from a mathematical point of view. It's so simple, isn't it? It looks awesome. It's also totally confusing and useless, all at once. It doesn't tell us how recursion works. It doesn't tell us how we can use it, how we can solve a problem, and why we would even bother in the first place. So what's a better way? Let's take a simple example. Let's suppose we want to write a function, not sum, which adds all the numbers from n down to 0. In Haskell, it's super easy, because we can just write this. This is a valid Haskell program. Well, not the dots, but you can just write more lines, okay? I leave it to your imagination. It just says for every number what you have to add up. But we can build on that, okay? we can notice that actually for every line, the line above is included in the line below. So we can reuse the line above. Okay, that's more compact. So then the next thing we notice, all the lines except the first one, they're basically the same, except for the number. I mean, you're experienced developers, so if something is the same except for one thing which varies in the same way, we use a variable, right? And then we are left with two equations, and that in fact is the recursive Haskell program to do the computation we set out to do. So this is a constructive way to actually get to that recursive program. Now I know this is a super simple example, but on purpose I want to make it super simple because I don't want to distract from the point with the complexity of the example, right? This is how you can write recursive functions in Haskell, also more complicated recursive functions in Haskell. And even more, if we want to know how this definition works, we can just write it out. We take a concrete argument, and then we substitute left-hand sides for right-hand sides. And we do that until we can't do it anymore, which is when we have to hit the base case, and then we can add it all up. And this is not just kind of like, this is it written out on paper. This is exactly the semantics of that Haskell program. This is exactly what your computer does when it runs it. This is the semantics of the program. So this illustrates a concept. It illustrates the concept of recursion, and it gives us an idea for how we can get to a recursive definition in the first place. And yes, super simple example, but this doesn't just work for recursion, it works for more complicated forms of recursion. It also works for higher order functions, parametric polymorphism, type classes, even for categorical structures, stuff like monads. So this approach scales to all kinds of abstractions. It's basically a way of introducing abstractions in a constructive manner, in a manner where you see what happens, as opposed by giving you definition and letting you figure out the rest by yourself. All right, that's examples. So how about these design patterns? When I say design patterns, I don't mean exactly what you would recognize as design patterns in object-oriented programming, although there's some similarity. What I mean is that, for example, with recursion, let's stick with recursion. Recursion is on one hand so simple and on the other hand so general. Given a problem, there's so many ways in which you could write a recursive function that when you're not used to it, you don't even know where to start. And in fact, even if, for you people who are all experienced developers, recursion in Haskell is still an obstacle, because in other programming languages, use recursion when you traverse a tree or something once in a while, but usually you try to use a loop or some other way. But in Haskell, for example, in most functional programming, recursion is like the hammer used for almost everything, right? So the recursive definitions are quite a bit more sophisticated. So it's important to give some guidelines, like what are the different types of recursion, because there are actually not that many. So how can we get at that? Well, we can have one recursive function. So this function is, again, a Haskell function. It takes a list, and it applies x times x to every list element x. So it squares all elements in the list. Now, we can have a second recursive function. Looks quite similar, but it applies this toUpper function, which takes a character and turns it in uppercase character, to every element in the list. Now, if we look at these two definitions, they are actually, except for the identifier, the names, they're basically the same. So we can make a more general, like a pattern, where whenever we want to do something for every element in a list or other data structure, we can just use this type of function and just worry about writing the orange bit and not everything else. That's important because if you have a programming problem and you know you have this empty screen on your editor and the cursor is going beep, beep, beep. This is the worst bit, right? How to get started. If you already know you can use this pattern, you only have to fill in the orange bit. That's much more reassuring. At least there's some code. And again, you may say, well, this is just experienced functional programmer now goes like, this is just the map function, what are you talking about? Yeah, it's just the map function, but map function is more complicated, it requires higher order functions and so on. So before you even get there, it's important to give people these structures. And not just for map, of course, there are all kinds of recursive idioms, and it's important to present them all, categorize them and say, in these different situations, use this type of recursion, this type of recursion, this type of recursion, and you cover 95% of all recursive programming problems this way. It's much easier to get started. Okay, so not just this is what you can do, but how do you get there? All right. So that was the first two. What about this tight feedback loop? So now one invention of functional programming right from the beginning with Lisp was REPLs. Read, eval, print loop. You have like a command shell where you can type expressions of your programming language and it gives you answers. Now we can do even better. And we can give continuous feedback while you write your program, and that's super helpful. So this is just part of a screencast from this tutorial, online tutorial which I mentioned earlier. So it's same example, okay, but the important thing is not the definition, which you know by now. I mean, you're experts at Recursion Haskell by now, I hope. But that we can run it right away. So there's just going to be one more case, but not only that, we can run it right away. So we call nutsum on these different arguments, and that works just fine because we covered those cases, but 50 doesn't quite work because we haven't got a case for 50. All right, good. So now we notice what I said before, that we can reuse the definition of the line above. So we can just rewrite these equations. And then we would expect, I mean, if I'm right, and this is the right way to go about writing these functions, then the results shouldn't change. I mean, it's not a proof. This is like a super simple test case, but gives you immediate feedback. You're on the right path. Okay, the transformations you're doing to your program actually go in the right way. And then when we notice that we can actually introduce a variable, get rid of all these superfluous equations, then again we see that the results, they are the same. But not only that, the call to 50, which didn't work before, works suddenly. So obviously this is the general definition. So the important thing here is that there's no you write code for half an hour and maybe get syntax mistakes for another half hour, and then you compile stuff and then you run stuff, but you get feedback right away. Now this is not particular to functional programming. You can in principle do this with any programming language, but something which is quite in the tradition of functional programming, and I think we can supercharge this in this way, playgrounds like this. Okay, so this is what I mean by tight feedback loops. So we can use tools to make it easier to learn this stuff. And one special thing about functional programming is the equations. Everything is so-and-so equals so-and-so. And you can replace one thing being equal by another thing being equal, and you'll never break your program. In contrast to C, Java, and every programming language which allows you to have side effects in the middle of things. So this approach works even with big programs. Okay, so that's tight feedback loop. So how about the visualization? Again, recursion. Today's recursion day. So there's this concept of fractal trees, which really beautifully represents recursion visually. And as I mentioned before, for pure functional data structures, this works in a very general way. You can visualize them very well because, again, there are no side effects in the construction. There's no destructive bit. So the idea here is we start with a square, and the top thing is the base, and then we draw a triangle on top, and the two sides of the triangle, that's where you put the next square. And another one, and another one, and another one, and another one. And you get a tree-like thing. Right? So we can do this in code. Now here, I come over here because I was using the other screen. So here we see fractal tree, forget all the other stuff. Recursive looks like a start to a recursive function, but this is not recursive. It's just one list element. Hence, we only have this one thing over there. Okay. So that's good. So now we go and we add a recursive call to the fractal tree function. And as we do that, we see that the tree grows, right? But we have only one recursive call, so it's linear as the recursion depth increases. So what we can do, we can just take this recursive call and copy it. So we get two recursive calls, but we use that second call for the second roof of the triangle, and lo and behold, we get a tree. Okay? So then when we increase the recursion depth, the tree grows. So this is really the recursion of that function visualized, right? And actually, these trees, you can, if you play with the parameters, you can do some really nice graphics. So it's also fun. And it gives a visual understanding and intuition of how the computational structure works. And you can do that for a lot of things in functional programming. It's a really good way to build an intuition. So that's the other tool which I think is really useful. It's much better than starting with the math. Start with some graphics and then do the math later if you like. So one contentious issue, which you may, I'm sure, this is like you take a group of developers and then you ask this question. Should we use strict type systems? Yes or no? Fight! You'll have fun with that every single time. So, you may wonder, I mean, functional programming makes a lot of fuss about type systems, right? But then there are languages like Lisp, like the first functional programming language, which didn't have a type system. So, should we use type systems? Shouldn't we use type systems? Maybe you should ask why. Why does anybody use a type system? You must have an opinion, I'm sure.
Compile time safety.
Compile time safety. So, any other opinions? It's a good one, of course.
Discoverability. Proving your program semantics.
Proving your program semantics, that's hardcore.
To get in your way.
To get in your way, dissenting opinions.
So you can actually define all the states if you want?
You define states, that makes sense, yeah. So, you went further, but otherwise it's kind of like getting this direction, right? Like the type system is kind of, it's there to, don't do this, it's going to crash your program. Bad programmer. But think about it, an architect, right? Not today. Today an architect, you see a D program and everything, no. Like 20 years back. Want to draw a diagram. They've got a ruler. Now this ruler, is this like constraining the person? I can only draw straight lines with this thing. No, it's a design tool. And the same for a type system. You shouldn't view a type system of something which doesn't let you do certain things. If you use it like, you can use it like this, and yeah, you get compile time safety and you constrain your states, but type systems are much more beautiful. They can help you to write your program instead of just checking that your program does certain things or doesn't do certain things. In fact, so let me get back to Filets and Filets and Filets and Krishnamurti's work, which was this original paper. And remember the Bootstrap Program, which they did at high schools and middle schools. That came with the paper was actually explanation of the approach they took in this book called How to Design Programs. And I mentioned before they used Racket, or they're still using Racket for this. And Racket is a variant of Scheme, which is a Lisp-like language, so it doesn't have static type discipline. Nevertheless, in this program, which is about in this book, which is about designing programs, they start by saying, well, you write out examples. Well, I mean, I said that a few times today, so we are on the same page. And then they say, you write out a type signature. But it's Racket, so you have to write your type system signature in comments. And then at some point, you write your code. And I mean, the type signature sits there, and you can try to correlate it to the program, but that's it. So why did they do it? I mean, I have to say they also worked on contracts and stuff to try to get some checking out of that. But they did it because it's a good way to write your code. They wrote the signature before they wrote the code, because writing down the signature is a good way of getting towards writing your program. It's a good way of designing a program, even if there isn't a compiler to check the signature. So now, how much better in a language which does check it? You get even more benefits. So if you're interested in this, there's actually a talk which I gave at YOW Connected 2 years ago. And it's not about Haskell, it's all about Swift. But Swift, you may know, is Apple's new language, which is a hybrid object-oriented functional language. But it has a very powerful type system. And you can use the Swift type system beautifully to help you with your program design. And so that gives you, if you want to know more about how to do this, the URL has not only slides but also the videos from the conference, so you can have a look. So then people go, but okay, maybe I can somehow use it to design my program, but when I do experimentation, prototyping, then I want to run my program, but then I get a type error and the compiler annoys me and I have to fix this first, and otherwise I can't do tests, or when I refactor, then it takes ages to compile it again. Well, truth be told, this is a problem with your tools. It's a problem with your compiler. Let's look at Haskell. So GLC has something we call deferred type error messages. So here we have a program. The top thing, data, is a definition of a data type of expression trees. It can be addition, multiplication, or integer literals in the opposite order. And then we have an eval function, which for each of these cases tells you how to evaluate it. And on the right-hand side are 3 different examples of doing the evaluation, with first only integer literal, then addition, then everything. Now what if we want to add equality? At the moment, the eval function returns an int. But if we have equality, it has to return a bool too. So we have to change the type of the function. So we introduce a new type, value, which returns either an int or a bool. Right? Value can be an int or bool, one of the two. And you can read the vertical bar as or. It's int or bool. But now I have to change the type of eval. And look what happens. We get a type error. So, but I'm not fast. I'm just going to fix the first case. the case of just the integer literal by returning not just the int, but the int val of int. And now, if you look at the right-hand side on the playground, look, the first example runs. That's the example which only uses an integer value. But there is still a type error, of course, because the second case, is still wrong. And if you look at the exception on the right-hand side, well, it's just a type error, but as an exception. So what's the idea here? The idea is very simple. If your program has a type error, then that means that part of the program where the type error is, you can't run. But that's true in Python too. You just get an exception when you actually get there. Why shouldn't you be able to run the rest of the program? Except maybe your compiler is too stupid to generate the code. But that's a compiler construction issue, not a fundamental type system issue. So how about we fix this next example? So we add the case expression to pattern match on the two int vals, which we should get if we want to add them, but maybe we don't know what to return as a result. And then what we do, we just put an underscore. What underscore means, I'm not quite sure. Compiler, can't you help me? And then you check the error message, and the error message says on top, a hole. There's a hole in my program. But the hole has a type. Colon, colon is Haskell speak for, on the right-hand side of colon, colon is a type. And it says value. So value is the new data type we introduced. And this new data type we introduced, value, has only two cases. Can be an int or bool. Now I'm implementing the addition case. Which one does it have to be? Int. There's no choice. Really, this program writes itself. So we put the int case, int val, but then I'm still not quite sure how to continue. So I put a hole again, and now if I look at the error message, then it says, well, the thing should be of type int, the argument I give to int val. And lo and behold, there's also a list of all the variables in scope. And there are only two variables, v1 and v2, which are of type int. That's the only stuff I can put in there, right? And I want to do an addition, so I probably want to add the two. And, well, let's try that. So I add these two variables, v1 and v2, and yay, one more equation done. And then we just do the same thing for the last case. So look at that. With those holes, we didn't have a choice, right? Once the compiler told us what type we had to put there, there was very little choice. And it was quite clear from the context what we had to do. So type error messages can help you write your program. And the stronger your type system, the more information, the better the compiler can help you. Okay, that's what I mean by types. Use it to design your program, not just to complain about the compiler giving you a hard time. All right, so this is already about tools, right? Every compiler for a language with static types should allow you to run the program even when it has type errors. Not for production code, but as an option for debugging, testing, refactoring, that during refactoring you can test the things which you have refactored, even if some are still type incorrect. Should be able to run the rest, right? So now I'm going to make a statement which is going to make some people unhappy. The one way to get everybody to fight in the room is to ask, do you want a type system or not? The other thing you could do is like, what's your favorite editor? And really, I added a modern one as well, but a lot of the stuff we are using is quite old. Right? Remember beginning of this talk, I talked about structured programming, object-oriented programming, now we do functional programming. So a lot happened in programming languages over those years. Do you want to tell me that all we can do in tools is the same stuff we did 30 years ago? It's not very plausible that this is the end of the road. We've reached the optimum, we can't improve anymore. Really. Do you know this guy, this website, and who's behind it? This website is of a chap whose name is Brad Victor. He was at Apple and wherever, I mean, he was at all kinds of places. Now he's at Y Combinator Research. And go have a look at the website, at those talks. He has nice ideas. I mean, he has these concepts of how programming environments could work. And they're very interesting ideas. And some people have started to try to put them into practice. So, for example, two other people from Y Combinator Research, they have this experimental programming system which doesn't just let you evaluate things while they're running, but gives you other information about intermediate values and call trees and so on. And it's all, when you change your program, this stuff changes right away. Right? It's not like a profiler, you do it and then we wait half an hour. Immediate feedback, tight feedback loops. Or you've seen like the app I used for the Haskell programs, Haskell for Mac, has this idea of playgrounds which evaluate all the time. You see what's happening immediately. And it's not just Haskell for Mac. Which we are using, for example, we have used this at UNSW for teaching, and it's, as a teacher, it's great, and Haskell for Mac users like it as well. But Apple has this idea of playgrounds as well. So for Swift, Xcode has Swift playgrounds, and then Apple has introduced this Swift Playgrounds app for iPad, including mechanism to write tutorials in it. And who has seen that? Who's tried it? Few people. Well, everybody who's kind of can get an iPad, steal it from your kids or whatever. Have a look at the app. It's really nice. Again, it's this idea of you do something, you get immediate feedback, and Apple has put quite a lot of energy into the situation where a lot of people are calling for, like, every kid should learn to code, right? And then parents go to school and say, you have to teach our kids how to code, and the teachers go like, I have no idea how to code. How can I teach it, right? So Apple has seen this opportunity, and they've actually done a lot of teacher training. They have developed a curriculum for Swift, obviously, and they're using this app, and it's quite nice. So I use my kids as guinea pigs, you know. So my now 13 years, he was 13 years at the time, not this summer, last summer. I had him do all the tutorials in Swift Playgrounds. And this summer I wrote an iOS iPhone app with him. So it works, right? So I think there's a lot we can do with tooling. It's just like people a bit lazy pushing tooling forward, and we still use the same stuff as we did a long time ago. All right, so that's my point. Example-driven strategy. You have to start bottom up. Don't start with the abstraction, start with the concrete, work your way up. Very important to introduce design patterns to guide people to how to use this stuff. Don't just put it out there. There has to be concrete recipes for how to use different styles of recursion, polymorphism, all this stuff. Tight feedback loops and visualization helps a lot. And well, if you want to learn Haskell, you see there are lots of options now. You can do online tutorial, you can go to Tony's course, you can come to Lambda Jam. It's all happening. Thank you very much.
Anybody have any questions?
Sam.
Yes, I've heard Tony Morris talking before about teaching Haskell to his kids. I'm wondering if you know very much about teaching Haskell to kids. So there's lots of stuff out there for them, like code.org and Swift Playgrounds for teaching imperative programming, loops and conditionals, but there's not a lot of content out there for just teaching pure functional stuff. Is there anything that you know of that's sort of focused towards kids that we could use?
Yeah, you're totally right. So with for example, Swift Playgrounds, I said I'm using it, and I like the app a lot, and they've really thought about how to teach the individual things, but the approach I don't like very much. It's very state-driven in the beginning, and there's not so much out there. I mean, the guy, the 13-year-old, the guy who did Swift Playgrounds with 13, we started him on Haskell when he was 9, so it was okay. I think it's the perfect age. At that age, the kids at school, they've learned about functional definitions. And they use now 2D coordinate systems because often they want to do some gamey kind of thing. So it's good to know coordinate systems, functions, and you said, I mean, NatSum is really easy. It's kind of, for a kid, it's kind of like, what's even the deal? And they don't overthink it. And well, you write it out on paper, it does exactly the same thing. But there's very, very little material. So there's one thing, there's Code World. Is kind of an online environment to do Haskell, and the person, I forgot his name, something Smith, who did Code World, he has used this specifically. He's developed a thing to teach middle school, I think, level, just for fun, I think. And I think he has some material around it. But there's not a lot out there. That's absolutely true.
Yeah, I've used this awesome app called Haskell for Mac.
Thanks.
It's more, you know, the examples and the code.
Yeah, the curriculum, really. So, I mean, when I taught Leon, so I've got a GitHub repository, which if you go to my GitHub account, and it's something code, Let's Code, I think it's called, the repo. And this has some even older stuff using gloss and so on, but it has notes which I use to describe. I actually, at some point, I didn't just have Leon, I asked him to bring a few friends, so I had 10 children. 10 to 11 years old, and I kind of tried to teach them together. And we did Haskell, and it was fun. And yeah, so there's some notes in there on the steps I took, what I started with, and so on. But this is all kind of quite scattered material. I don't think there's a really nice thing. I'm not aware of anything which is really like a full thing you could take and just do. Yeah. So more work to be done.
If the programs you write are heavily based on accessing a relational database and getting rich data structures into your program and finding the right use case for them, would you say that type of program is fit for purpose for use in the functional programming pattern? Because I get the sense that functional programming is very suitable for if you're trying to create complex calculations and computations, but to me it doesn't really translate into that world where you don't really necessarily need that computation, but you just need to get data from a relational database.
Yeah, so you can totally use functional programming languages for that very well. In fact, I mean, to a certain extent, SQL is actually a functional programming language. It's a domain-specific language, but it's really a functional language. And usually there's quite a mismatch between SQL and the language you use it in. And in a language like Haskell, you can make this much more seamlessly. You can actually use a subset of Haskell as your SQL queries and even have type safety, get the type checker to help you design your SQL queries and stuff. So that's totally possible. And if you look at the Haskell libraries, then there are X different database libraries out there. So generally, I mean, data processing is something you can do very well. You can do this more mathematical numerical stuff, but you just plain data processing, data science-y kind of things, not just the numerical things, but also just kind of having big data sets, looking for things, searching for things, combining things, works beautifully in functional languages. And yeah.
One more question.
Kind of related one. I'm a bit of a skeptic of can you pull this back to business examples, so a little bit related to that then. One of the toughest things I've found is to do things like have variations on a GUI where it's going to vary. It's kind of like the pattern matching problem. We've got chunks of it varying depending on the nature of the data that's there.
Mhm.
So is anybody documented kind of like how to apply from Haskell and FP in a business programming sense? It's an extension of those sort of things with examples, because most of the examples I see tend to go down the data structures and mathematical sort of side of things.
Yeah, so I mean, one problem which we're definitely having is a documentation teaching problem, in that there's a lot of beginner material along those lines. Then there's really high-level stuff which you find at PL conferences or something like that. And there's very little in the middle. And this is the reason why we originally created Lambda Jam, to provide information in the middle, not in a written form, but in the form of a conference where you can go, you can actually talk to people, you get people who actually use this stuff in production, and they can tell you their experiences, what works, what doesn't work, and so on, which I think at this level is much more convincing than just having a write-up. And slowly we are getting more written things at the intermediate language level as well, but there's still huge gaps, as you are saying. That's totally true. Nevertheless, I mean, so I'm mostly working for a software consultancy, Tweak.io, at the moment, and Tweak is, most of our projects involve functional programming. Usually it's a mix of things. It's Haskell and Java, Haskell and R, other things combined. But we see the uptake at the moment is enormous. And Tweak plays a lot in distributed systems, numerical computing, data science, biopharma, that kind of domain. But there is also a lot of use of functional programming in especially investment banks. Also in the blockchain space is very popular. In fact, the project I'm working on at the moment is with IOHK, which is one of the blockchain companies. And so this technology is very applicable to those domains. It's just that there's not a lot of information out there, except in the heads of people who've started doing it. But that's at the stage where we are at the moment. It's unfortunate. I totally see it, but yeah.
It's unconvincing. Because it's great, it's wonderful. No concrete examples of how to apply those sort of problems.
Right, but by now we have, I mean, there are projects, lots of projects out there now. It's just at the moment we're at the stage where you have to know somebody you can talk to who has got this experience. But there are quite a lot of people with that experience out there by now. So it's getting easier, and I think the conferences and so on, that helps. It's a bit easier than writing a book. Less time consuming. Yeah.
Sorry, just a quick one. Where are we on that diffusion curve, do you think?
It's hard to say. So in my opinion, I think we are in the transition from early adopters to early majority, which is why it's getting interesting now. This is why we haven't thought about it like this when we introduced the Welcome to FP Day. It's just more and more people asking, couldn't you do something like that before the conference so I can come too? And from that demand, we did that day. But I think the reason is because we're at that stage.
Thank you, Manuel.
Thank you.
Thank you for coming along tonight, everybody. Also, big thank you to Bankwest for giving us somewhere to sit so we're not out on the street. And also to DDD Perth for being our community partner for this evening.